In this problem, we're given the equation y equals x squared minus 4, and we are to draw a sketch of the graph, determine its horizontal and vertical intercepts, and then determine if it has any kind of symmetry. To find the horizontal intercepts, that would be where the graph crosses the horizontal axis, usually called the x-axis. To do this algebraically, the technique is to replace y with 0, because we know any point on the horizontal axis, which is where you'd be at if you were a horizontal intercept, has a y value of 0. So solving this equation for x, I add the 4 over, and I get that x squared equals 4. From here you can either surmise, since 2 squared is 4, that one of the answers is 2, and also the number negative 2 quantity squared is 4. So you may be able to tell just from that negative 2 is another x value that satisfies this equation. To solve this algebraically, the inverse of squaring is to take the square root. Here you may have been told to simply simplify this down as x, and to put a plus or minus in front of the radical here to consider both the solution 2 and the solution negative 2. Algebraically, you may be interested to know that since we're not assuming x is positive, that the square root of x squared actually is not x, it's the absolute value of x, and the square root of 4 is simply 2. So we're really solving this equation algebraically, which leads us to figuring out what numbers, if you were to take the absolute value, you would get 2, or to put it another way, what points are 2 units from the origin? Well, that would be x equals 2 and x equals negative 2. So however you look at it, you get that negative 2, 0 is one horizontal intercept, and that positive 2, 0 is another intercept. To find the vertical intercept, this is much easier. The vertical intercept is where the graph crosses the vertical axis, usually called the y-axis, and if you were a point on the y-axis, it's your x-coordinate that's 0, because you move 0 units in the x direction, and that would leave you on the y-axis. So the technique, algebraically at least, of finding a vertical intercept is to replace the x value with 0 and find the value of y. So replacing x with 0 and evaluating the equation, 0 squared is 0, 0 subtract 4 is negative 4. So when x is 0, I get that y is negative 4. So 0, negative 4 is the vertical intercept. That would be the point right here. Finding the vertical intercept algebraically was easy, but it may be easier yet to just use your knowledge of transformations. So for example, had your equation just been y equals x squared here, the graph would have been a parabola whose minimum is at 0, 0. However, since our equation had a subtraction of 4, the graph gets moved down 4, and the new vertical intercept would move from 0, 0 down as in the following picture. Here's the graph of y equals x squared. The vertical intercept is 0, 0, but the graph of y equals x squared minus 4 would be the same as the red graph, but shifted down 4, making the new vertical intercept 0, negative 4. Notice also that the horizontal intercepts of negative 2, 0, and positive 2, 0 are also correct. Now I'd like to discuss the last 3 questions. Is the graph of the equation symmetric with respect to the horizontal axis, or the vertical axis, or with respect to the origin, or perhaps none of these? It turns out that the graph has symmetry with respect to the vertical axis. What this means is, if you were to take a piece of paper, for example, and used finger paint to draw this picture, and you folded the piece of paper about the vertical axis, or usually called the y-axis, what would happen is that the graph would stay the same. The right-hand side of the parabola here, or the ink on the paper that looks like the right-hand side of the parabola here, when you fold the piece of paper, would fold over here and simply cover up the left-hand side, and vice versa. The left side of the parabola, or the ink that you use to draw the left side of the parabola, if you fold a piece of paper about the vertical line here, it would fold over here and just smudge on top of the right side of the parabola. So when you reflect about the vertical axis, the picture does not change. So this graph is symmetrical about the vertical axis. It is not, however, symmetrical with respect to the horizontal axis. This would be easy to explain. Suppose you drew this parabola with wet ink, and this time you folded the piece of paper about the x-axis, or the horizontal axis. What would happen is these 2 points would stay fixed, but the parabola would flip upside down. And whenever I draw something by hand, it comes out very crude. so I try not to do it very often. But it would look something like this, and it would give us a new graph, unlike the one we started with. Therefore, it does not have symmetry about the horizontal axis. In case you're wondering what it means for a graph to have symmetry about the origin, here is a better picture of what happens when you take the graph of y equals x squared minus 4, the red graph, and you reflect about the horizontal axis. We did that a second ago and said that the graph does not have symmetry with respect to the horizontal axis, so this was no. And it's because if you reflect the red graph about the x-axis or the horizontal axis, meaning we fold the piece of paper about this line, that the red graph would turn into the blue graph. It would be upside down. Since you get a new picture, it has no symmetry about that line. To be symmetric about the origin means that you would reflect about the horizontal and the vertical axis in either order, and if you ended with the same picture you started with, you would have symmetry about the origin. This is simply not the case for our graph, because we started with the red graph, reflecting about the horizontal axis turned into the blue, and then the idea would you'd take the blue graph and now reflect about the vertical axis, which I'm dotting now, and because it is symmetric with the vertical axis, folding the piece of paper about this line makes the left-hand side the right-hand side and vice versa. So in summary, taking the red graph, reflecting about both the horizontal and the vertical axis in either order, produces the blue graph, which is a new graph. So therefore, since I did not end with what I started with, the graph does not have symmetry about the origin. Let me show you an example of something that does have symmetry about the origin in case you're interested. This would be an example of a graph that has symmetry about the origin. I got this graph by graphing y equals x cubed. If you were to reflect y equals x cubed about the vertical axis, the right-hand side of the graph right here would move over here, and the left side of the graph of y equals x cubed would move over here. You'd get a new picture, so obviously y equals x cubed does not have symmetry about the vertical axis. But the question is, does it have symmetry about the origin? To find whether it has symmetry about the origin, you must reflect about the horizontal and the vertical in either order. So the next step would be now to take the blue graph and reflect about the horizontal axis. That would be this one. And if I did that, this piece here would move down like this and become part of the original red graph. And this part of the blue graph would reflect up, since we're folding about this line, and would move on top of the right side of the original red graph. So in short, taking y equals x cubed, the original red graph, and reflecting about the vertical and the horizontal axis in either order would produce the green graph. And since the green graph is essentially the same as the red graph, what we started with, that means this has symmetry about the origin.